So there is this really famous sentence in linguistics that was introduced by Noam Chomsky.
Oh, right, the green ideas one?
Yeah, exactly. Okay, it goes, colorless green ideas sleep furiously. And if you break it down, it flawlessly follows every single rule of English grammar.
Right, you've got your adjectives, your noun, your verb.
Exactly. You have an adjective, another adjective, a plural noun, a verb, and an adverb, all in the exactly correct structural order. But, I mean, if you actually think about it for more than a second.
It means absolutely nothing.
Right, it means nothing. A green idea can't be colorless. And ideas certainly don't sleep, let alone furiously.
Yeah, it parses perfectly, but the meaning is just fundamentally broken. It's a structural triumph, but a total logical failure.
And you, the listener, you've probably written code that does the exact same thing. Like code that parses perfectly, code that structurally looks like an absolute masterpiece in your editor.
But then when you step back, it makes zero logical sense to the computer.
Right, so today we are taking a stack of your Class 19 notes and Chapter 7 of your textbook to figure out how a compiler actually catches those, colorless green ideas before they ruin your program.
We are officially transitioning from the grammar of code to the meaning of code.
Which is huge. We are taking the raw structure your parser built and finally breathing some actual logic into it.
Yeah, it's the crucial bridge between human-readable text and machine-executable action. And just to set the stage, we're focusing strictly on the deep theoretical concepts today.
Right, the overarching architecture.
Exactly, the overarching architecture of semantic analysis. We are saving all the nitty-gritty implementation details for a future session.
Okay, let's unpack this by starting right where the previous step of the compiler left off. So the parser took our raw tokens and built an abstract syntax tree, or an AST.
Which is a great structural map.
It is, but the parser is guided by a context-free grammar, which is usually expressed in Backus-Naur form, or a BNF. And BNF is practically blind to the actual relationships between the elements it organizes.
What's fascinating here is that the parser is essentially just a strict spelling and grammar checker.
Right, like it confirms you wrote noun, verb, noun.
Yeah, it knows that an assignment statement must consist of, say, a variable, an equal sign, an expression, and a semicolon.
But it doesn't know that you can't, divide an integer by a toaster.
Exactly. It has no idea if the data types on either side of that equal sign are actually compatible, or, if you even initialize the variable before trying to use it.
It's just pure syntax, structure without meaning. And that brings us to this big split in language study, which is syntax versus semantics.
Right, semantics is the meaning. It's the actual logic of what the code is supposed to do.
And based on your class notes, semantics breaks down into two distinct categories. You've got static semantics and dynamic semantics.
Dynamic semantics being the runtime behavior, right? Like the things that happen when the program is actually executing in memory.
Exactly. But our mission today is purely focused on static semantics.
Which are the rules checked at compile time, right, without the program ever running.
Think about the rule in Java that requires a class name and its constructor name to match exactly.
Oh yeah, you can't express that in a standard BNF grammar rule.
No, not without it infinitely complicating the parser. Or consider type compatibility, like trying to assign a floating point number to an integer variable.
Or a character string to a Boolean.
Right. The structural requirements are completely impossible to express purely through syntax, but they are entirely verifiable through static analysis.
And catching these logical requirements before the code is converted to assembly and executes, that is what saves end users from catastrophic crashes.
Absolutely. If a compiler can guarantee that an addition operation is strictly happening between two integers, it doesn't have to generate all this bulky, slow error-checking code for the final executable.
It just runs.
It just runs. It provides this dual benefit, like a safety net for the developer during the writing phase, and a massive performance boost for the user during execution. But this creates a pretty interesting architectural problem. If the parser just gives us a structural AST and that tree doesn't inherently contain any of this logical meaning, how does the compiler actually enforce these rules?
Well, we have to force the AST to hold that meaning. We have to add to it.
And for that, the notes point us to a concept introduced by the legendary computer scientist Donald Knuth way back in 1968.
Yes. Attribute grammars.
Right. Knuth proposed a way to describe and check the correctness of static semantic rules by attaching metadata directly to the parse tree.
An attribute grammar essentially builds on our basic context-free grammar by adding three distinct mechanisms.
Okay, what's the first one?
First, you have the attributes themselves. These are the actual values or the metadata associated with the node in the tree.
So things like the data type of a variable or the value of a constant or maybe the memory location.
Precisely.
So it's like the
I like that, but decorating the tree is actually less like hanging static ornaments and more like wiring a circuit board.
Oh, interesting.
How so? You're attaching sensory pathways so the different branches can actually send signals to each other about what kind of data they are holding.
Oh, wow, yeah. That is a much more accurate visualization.
Because the second mechanism is attribute computation functions.
The logic gates in your circuit board metaphor.
Exactly. They specify exactly how to calculate those attributes based on the surrounding nodes.
Okay, and the third mechanism?
The third is predicate functions. Think of these as the circuit breakers.
The strict semantic rules.
Right. They enforce the required relationships between attributes. If a predicate function evaluates to false, well, the circuit breaks, the compiler throws an error, and your build fails.
So let's trace how these signals actually move through the wires of our AST, because there are two distinct directions this metadata flows.
Yes, synthesized and inherited.
Right. The first is synthesized attributes, where information bubbles up the parse tree from the leaves to the root.
So imagine an AST node for the expression x plus 5.
Okay.
The leaf node for 5 synthesizes its type, which is an integer, up to its parent, the addition operator.
And the leaf node for x looks up its type, realizes it's also an integer, and synthesizes that up as well.
Right. The addition node then takes those two synthesized types, runs its computation function to verify they are compatible, and then synthesizes its own resulting type, integer, up to the assignment node above it.
So this sort of grassroots bubbling up of information is how most basic expressions are evaluated.
It is, but logic dictates the information has to flow the other way too.
Right. If I declare a whole block of code as floats at the top, that rule needs to trickle down to all the individual branches.
Exactly. And this is the second type of flow, inherited attributes. These send information down and across the parse tree.
So if you have a declaration like, float XYZ, the type float is determined once at the parent node.
And that information is then passed down the tree to the individual variable nodes. So X, Y, and Z all inherit the knowledge that they are supposed to be floats.
The parent node basically dictates the context for its children.
Yes. But I should mention, reading through the textbook, actually wiring up a fully attributed parse tree in memory and constantly passing metadata up, down, and across millions of nodes.
Well, it sounds computationally massive.
Oh, it's got to be exceptionally heavy.
It is. In practice, modern compilers rarely build a fully decorated, completely comprehensive AST just for static analysis.
It's just too slow, right? Uses too much memory.
Exactly. But the concept of analyzing metadata across the tree remains universal.
So how do they do it without running out of memory?
Compilers usually use highly optimized side data structures to track these synthesized and inherited attributes. It maintains the underlying logic of Knuth's design without the sheer memory overhead. Okay, so if we are wiring this tree with sensory pathways to enforce what a node is allowed to do, the compiler first has to understand the fundamental identity of the ones and zeros it's looking at.
It needs a vocabulary for the data.
Which brings us to the biggest rulebook in language design, type systems.
Broadly speaking, a type system gives the programmer a way to make verifiable assertions that the compiler can automatically check.
It defines what a specific block of memory actually represents, like, are those 32 bits, an integer, a floating point number, a memory address, or a string of characters?
Right. And the textbook lays out 3 main purposes for type systems: correctness, expressiveness, and performance.
Correctness is pretty straightforward. It prevents invalid assignments.
Like, you can't assign a memory pointer to a basic integer variable.
Right. And flagging that at compile time prevents a guaranteed disaster at runtime. And expressiveness is also cool. It saves us from writing boilerplate code.
Oh, definitely. When you call a print function in Python, the language's type system infers whether you passed a string or an int and automatically formats the output properly.
Without you having to explicitly call, like, print string or print integer.
But the third purpose, performance, is often the most critical for compiled languages.
Okay, here's where it gets really interesting, because I want to push back on this a little bit, actually.
Wow, okay.
Yeah, I always thought type checking was just about avoiding those annoying red squiggly lines in my code editor. Like, it felt like a constraint on me as a developer. How does knowing if something is an integer actually make the compiled program faster for the user?
Well, If we connect this to the bigger picture, it really comes down to how hardware interacts with memory.
Okay.
Accessing main memory, like going out to RAM to fetch a value, is incredibly slow compared to the raw processing speed of the CPU.
Right. That makes sense.
So if the compiler can guarantee through a strict type system that a variable is a constant integer that will never change, it performs what's called constant folding.
Constant folding.
Yeah, it can load that value directly into a hardware register inside the CPU and just use it instantly, over and over, without ever requesting a fetch from main memory.
Oh, wow. So it's essentially a contract. If I provide the compiler with rigid guarantees about my data, the compiler rewards me by generating highly optimized, bare metal machine code.
Exactly. But not all languages enforce that contract the same way. The notes contrast safe languages versus unsafe languages.
Right, like C versus Java.
Yeah, in an unsafe language like C, the compiler essentially takes you at your word, even if your word violates the basic boundaries of the language.
So if you have an array of 10 items in C and you write a loop to insert 100 items into it,
C will just keep writing data past the end of the array, blindly overwriting whatever else happened to be in adjacent memory.
the classic buffer overflow. The language just says, well, you're the boss. I'll write those 90 extra items right into the abyss.
Which leads to silent data corruption and massive security vulnerabilities.
But in a safe language, like C# or Java, those boundaries are strictly enforced.
Right. If you try to write 100 items into a 10-item array in Java, the runtime environment intercepts the violation and throws an index out of range exception.
It crashes your program, yes, but it crashes predictably and safely, preserving the integrity of the surrounding memory.
We also see a massive divergence in when languages type their data.
Because we've been focusing on static typing, where the compiler verifies every variable's type before the program runs, then strips all that metadata out to make super fast assembly code.
But dynamically typed languages like JavaScript or Python operate completely differently.
Right.
In dynamically typed languages, the type information is actually stored in memory alongside the data while the program is running.
So the safety of an operation is checked right at the microsecond it executes.
Yes. This allows for incredible flexibility. I mean, a single variable can hold a string on line 10 and an integer on line 20.
But you pay a continuous penalty in performance, right? Because the CPU is constantly halting to check types on the fly.
Exactly. We also have the distinction of explicit versus implicit typing.
Explicit typing is the classic, intech ace equals 5. You are telling the compiler exactly what the variable is.
Whereas implicit typing lets the compiler act like a detective.
Like in modern C++A, you can use the auto keyword. You just type auto x equals 5, and the compiler infers, well, 5 is an integer, so x must be an integer.
It makes code much more compact, but it requires an incredibly robust static semantic analyzer under the hood to infer those types correctly across millions of lines of code without making a catastrophic assumption.
But to enforce any of these typing rules, the compiler has to actually know which variable it's looking at.
This is true.
Think about how often you lazily reuse the variable I in your for loops, or name a variable count in 50 different functions.
They share the exact same name, but represent completely different data in different scopes.
So what does this all mean? How does it tell them apart?
Resolving this is the problem of name resolution. It is the process of matching each use of a variable name to its proper definition.
And to accomplish this, the compiler builds a critical data structure called the symbol table.
Yes. The symbol table records all the semantic metadata we need to know about every declared variable, its kind, its type, its scope, and its memory location.
It's like having 3 contacts named Alex in your phone. You have work Alex, gym Alex, and sibling Alex.
Good analogy.
If you just yell, text Alex to your smart assistant, it doesn't know who you mean. The context, or the scope, determines exactly which Alex receives the message.
And the compiler manages this context through a rather brilliant mechanism. It structures the symbol table as a stack of hash tables.
Okay, a stack of hash tables. How does that work?
Every time the compiler enters a new scope, for instance, when it reads an opening curly brace for a function or a local loop, it pushes a brand new empty hash table onto the top of the stack.
Oh, I see.
When it encounters a variable declaration inside that block, it binds the name into that topmost table.
So when it needs to look up a variable, it starts at the top of the stack, the most local scope, works its way down.
Precisely. If you are inside a loop, it checks the loop's hash table first.
If Alex isn't there, it checks the function's hash table just beneath it.
And if Alex still isn't there, it checks the global hash table at the very bottom.
And the elegance of this design really reveals itself when the scope ends. When the compiler hits a closing curly brace, it simply pops the topmost hash table off the stack and discards it.
All those local variables instantly vanish from the compiler's context.
This entirely eliminates naming collisions. The compiler seamlessly manages global scopes, parameter scopes, and local scopes simply by pushing and popping tables as it traverses the AST.
The only reason your entire program doesn't collapse on itself when you reuse I for the 100th time is because the compiler is quietly pushing and popping those hash tables to protect you from your own naming habits.
That is incredible. So first, map the names. Second, check the rules. It's a fascinating architectural dance.
And conceptually, resolving these names is the absolute prerequisite for checking types. You cannot enforce a predicate function on the variable x to see if it's an integer until you have successfully looked up exactly which x the programmer meant.
And retrieved its metadata from the symbol table.
Exactly.
Well, that theory directly powers what you, the listener, are going to be building over the next week. We've got some specific deliverables coming up on the syllabus that transition this theory into practice.
Yes. Looking at the schedule, your first priority is Sunday, March 29th. Your journal entry for week 9 is due.
Right. Keep the 2-1 rule in mind. That's a minimum of 2 paragraphs of reflection and 1 proposed quiz question.
Then on Monday, March 30th, you should be skimming chapters 8 and 9 of the compiler's textbook.
But the absolute critical deadline is the B minor parser Lab 7, which is also due on Monday. You need that parser finished because, based on everything we just talked about, next week we are going to start decorating your trees.
If your parser fails to generate an AST, you have no structure to hang your semantic metadata on. And looking toward Friday, April 3rd, there is the Liskov video assignment with perusal annotations.
Right.
Engaging with the Liskov video and doing the collaborative readings on perusal actively builds the critical thinking muscles you will need. Writing semantic implementations requires a rigorous, almost painfully logical mindset.
It really does.
These collaborative discussions help train that exact cognitive process before you actually have to write the code.
So build the parser, tackle the readings, and prepare for the semantic routines. We've covered massive ground today.
We really have.
We started with the realization that structural perfection means nothing if the underlying logic is flawed. We explored how Kuth's attribute grammars allow us to wire up our syntax trees with sensory pathways.
We talked about how type systems create a strict contract between developer and hardware.
And how stacked hash tables elegantly resolve our lazy variable naming.
We've basically mapped the journey of how a compiler infuses a rigid structural tree with actual meaning and rules, ensuring that nonsense instructions never make it to the CPU.
But, this entire discussion about compilers inferring our intent and protecting us with implicit typing, it raises a rather wild question about where this is all heading.
Oh. Where do you think it's heading?
Well, if compilers are getting so smart, like automatically deducing data types, managing memory boundaries, and inferring what we mean based purely on context,
right?
How far are we from compilers that don't just check our semantics, but actively write the semantics for us?
That is a fascinating trajectory to think about. I mean, as languages become increasingly safe and implicitly typed, at what point does the language understand your program better than you do?
Exactly.
If an AI partner is integrated directly into the semantic analyzer, translating plain English intent into strict static rules behind the scenes, the traditional role of the programmer shifts entirely. Does the pursuit of absolute safety at compile time actually limit our ability to express truly novel, if dangerous, ideas?
Does the grammar of code even matter anymore if the compiler understands the concept of what you want before you even type the syntax?
It's the ultimate evolution from syntax to meaning.
Soon, we might just be handing the compiler our green ideas and letting it figure out how to make them sleep furiously.
That's a great point to leave off on.
Thank you so much for joining us on this deep dive. Keep exploring your class notes, get that B minor parser finished this weekend, and we will see you next time.